Hello, George Romanic here. Welcome to Fundamentals of Weather and Climate. To describe dew point, the easiest is to start with an example that will right away tell you immediately what it is. We saw this graph many times. If we have temperature here, and here is saturation, water vapor pressure in the atmosphere, then we know that this dependency looks like so. It's a nonlinear function given by the Clausius-Clapeyron equation that I discussed in great details in my video on the saturation vapor pressure. Now, suppose that temperature is 15 degrees Celsius. Suppose this is the temperature. And suppose that actual partial water vapor pressure is 15 hectopascals. Let us say that 15 degrees is here in Celsius. Now, if I go up, I will meet this line, and I will go here, and I will meet ES. This is ES of 15 degrees Celsius. This looks like that line FAFO. If you know, you know. Now, it happened that Professor Romanic knows that saturation vapor pressure at 15 degrees Celsius is 17 hectopascals. Okay? So I know that this value is equal 17 hectopascals. But I just told you that the actual water vapor pressure in the air is 15 hectopascals here. So what I'm telling you here is that the amount of water vapor in the air is such that the pressure of water vapor is 15 hectopascals. To get saturation, we need to go all the way to 17 hectopascals. So how can I get saturation? Two options. Option number one, add more water vapor to the air to reach 17 hectopascals, you will get saturation. That's not so interesting in this video. Option number two, key statement. Do not add water vapor to the air, but decrease temperature of the air. How much should you decrease temperature? Look at this beauty. Decrease temperature for this much to reach this line. And when you reach this line, you will have saturation despite the fact you did not add or remove water vapor. What is this value of temperature? This is dew point, TD. And of course, this value of saturation vapor pressure is 15. I just told you, 15 hectopascals. So, what is dew point? Dew point is temperature to which we need to cool air to get saturation without adding or removing water vapor and having pressure constant. So, we can therefore see that this T, which in this case is 15 degrees, minus TD, dew point, tells us a lot about the water vapor content in the atmosphere. Because if T is equal TD, that means that the air is saturated. If T is larger than TD, the air is unsaturated. In the example I gave you, the air was not saturated. We could make it saturated by decreasing temperature to dew point. In that case, T equal TD, and we will have saturation. In this particular case, how much do we need to decrease temperature? If my memory serves me correct, I think that temperature for which saturation vapor pressure is 15 hectopascals is 12 or 13 degrees. So in other words, from 15 degrees we need to decrease temperature for a few degrees to get saturation. I cannot now remember exact values, you can find it online, but you understand the concept. What else can we say about dew point? Many things. It's very important quantity. You can see from here ES of TD, saturation vapor pressure of dew point is actually the partial vapor pressure of water vapor in the air. This is very clear. This is exactly what I demonstrated here. Because if I take dew point and I go up and I meet saturation vapor pressure, then that saturation vapor pressure associated with dew point is this blue, is the actual water vapor pressure in the air. So that means further that if we connect this with the previous video, you saw that relative humidity is E divided by ES as a function of T times 100. Well, I could also now say that relative humidity can be expressed. What is E? E is saturation vapor pressure as a function of dew point divided by the saturation vapor pressure as a function of T. And of course, we always multiply by 100 to get percentages. But you can see if you now have instrument that is measuring dew point and instrument that is measuring temperature, then you can find relative humidity easily using this line and this relationship over here, which is very useful and often used in atmospheric sciences, meteorology, and practical calculations of relative humidity. You can also see if dew point is large, then there is a lot of water vapor in the air. Because if dew point is moving to the right over here, then you are somewhere in this region over here, and that means the amount of water vapor in the air is very very large. And as I just said, if dew point and temperature are the same, we have saturation. So what I told you here also means, this is another very important thing in this video, is that I could have plotted this graph in the following way. You see, I have ES as a function of temperature, but I could also plot this graph as E as a function of TD. It is the same. Okay? Because, I will now repeat myself, I told you that ES of TD is actually E. So you can read this graph in terms of connecting ES to T, or you can read this graph in terms of connecting E with TD, whatever you prefer. And some books indeed give you this graph where you have these variables depicted the way I did it here. So this is dew point, temperature to which we need to achieve to have condensation in a parcel of air if we are not removing or adding water vapor and not changing pressure. What is frost point or frost point temperature? Let's erase this and discuss it. We saw in previous video that we can have the phenomenon of supercooled water. So if here I have saturation vapor pressure, and here I have temperature, and here is 0 degrees Celsius, then the line that we just discussed looks like this. But how about negative temperatures? So here are temperatures below 0 degrees Celsius. When temperatures are below 0 degrees Celsius, let me improve then this line splits in two. We have continuation that is associated with supercooled liquid water, and here this represents saturation vapor pressure with respect to liquid water, which is supercooled. What is supercooled water? Watch my previous video. But we can also have graph that we do have a line that represents saturation vapor pressure with respect to ice. Because below 0 degrees Celsius we can have ice and we can have liquid water. Now let's just repeat exercise that we did in the previous slide. So if we have some value of partial pressure of water vapor associated with this temperature T, how can I get saturation? Well, you now have to ask me a question. Do you mean saturation with respect to ice or saturation with respect to supercooled water? I can get that saturation by decreasing temperature, both of them. So I start decreasing temperature. I start decreasing temperature and I first hit yellow line. When I hit yellow line, this is called frost point or frost point temperature. If I continue, only then I will hit black line somewhere here. And this would be dew point with respect to supercooled water. So you can see that the frost point is always larger than the dew point with respect to supercooled liquid water, okay? For negative temperatures. This is for T below 0 degrees Celsius. If temperatures are above 0 degrees Celsius, then of course there is no frost point. Frost point is equal dew point. There is no ice above 0 degrees Celsius. So what is frost point or frost point temperature? Frost point is temperature that we need to reach or cool down parcel of air to get saturation with respect to ice. Dew point is saturation with respect to liquid water. Frost point is saturation with respect to ice, and then consequently it only makes sense to define it for negative temperatures. And you can see that in a negative temperature regime, you shall first reach frost point and only then you will reach dew point. That's why in spring and fall seasons, when we have low temperatures and cold nights, cold mornings, you wake up, you can see frost, not dew, because if temperatures are low and low enough to have transition of water vapor, well, that transition will first go into ice, namely we will have deposition of water vapor forming frost rather than condensation and forming dew. That also means, extra important, that frost is not frozen dew. Frost is deposition of water vapor molecules from the atmosphere on some objects, but not freezing of water that was already on those objects. Similarly, dew is not water that came out of these objects, either leaves or windows or branches, trees. That's not dew. Dew is water from the atmosphere that condensed on these objects. When did it condense? When temperature reached dew point. When did it form ice crystals? When temperature reached frost point. That's it for this video. Please make sure to like and subscribe, share this video, study atmospheric sciences, and until next lecture, goodbye.